In this video, we are going to implement GraphQL-over-WebSocket subprotocol using Ballerina language. The GraphQL-over-WebSocket protocol defines a standard way to execute real-time GraphQL subscription operations over a WebSocket connection. We will be setting up a WebSocket service that fully follows this protocol, handling real-time subscriptions using simple, elegant Ballerina code. Hi everyone, I am Ayash and I am excited to walk you through this full process. Let's dive right in. This is the public markdown file that defines the protocol. In this protocol, messages are structured as JSON and they are stringified before sent to the network. First, take a look at what are the different message types used in this protocol. We have connection init messages, connection act messages, ping messages, pong messages, subscribe, and so on. Each of these plays a specific role and we are going to break them down one by one. But first of all, let's see how to define these message types in Ballerina. Here we have simple Ballerina project. We define the messages in the types.bal file. Each message type model has a record. These records specify the fields that each message should contain. Let's start with the connection init record. Here you can see we have two fields. A type field which is set to WebSocket init and an optional payload which can hold additional information. The type is a keyword in Ballerina, so you have to escape that using a single code. Similarly, you can define connection like ping pong and so on. Here you will see we have WebSocket init, WebSocket act, WebSocket ping. These are actually constant. They are defined in separately to make the code more cleaner and easier to manage. So instead of hard coding strings everywhere, we simply use these constant when we want to define our message types. This approach keeps our code clean, consistent and much easier to manage. And then we have the rest of other messages. Next, let's take a look at how to handle closing the WebSocket connection in specific situations. Let's talk about how we are closing the WebSocket connection. In the GraphQL or WebSocket, when the client violates the protocol, the server needs to close the connection with a meaningful status code and a reason. In Ballerina, we have two types of close frame records: predefined close frame records and custom close frame records. Predefined close frame records are well-known close frame calls with their descriptive reasons. But in this case, the protocol defines its own close frames. Let's see how we can define a custom close frame record. Here we have domain initialization request record, which inherits from WebSocket custom close frame, and it contains two fields: status code, which is set to 4429, and a reason saying domain initialization request. Here the status code can only be 4429, so we can put 4429 as the type instead of integer type. Similarly, we can see unauthorized close frame record, connection in timeout close frame record, and so on. Similarly, we can define unauthorized close frame record, connection init, timeout close frame record, and so on. Now to make our code even cleaner and easier to use, we have also defined some constant of these close frame records. Here you can see too many initialization request, unauthorized, and connection init timeout. By doing this, whenever we want to return one of these close frames in our service, we can simply return these constants. Now we have defined all the message types we need. Let's see them in action. Here we have our WebSocket service. In Ballerina WebSocket, there is a concept called custom remote dispatches. This allows us to dispatch incoming messages to different remote functions based on a specific field in the message, usually the message type. Well, if you remember, every message we defined had a field called type. For example, in a connection at message, there was a field called type which is set to connection act. By checking this type field, the WebSocket service can figure out exactly which remote function should handle this message. Now the next question is, how does the Ballerina WebSocket which fields to look at? That's where the service config annotation comes in. In In the service config annotation, we set an attribute called dispatcher key. This tells the WebSocket dispatcher look at the type field in the incoming message and based on its value, call the machine remote function. Alright, now let's dive deeper into how each of these remote methods work. Let's take the connection init message as an example. When we receive a connection init message, it will be dispatched to the onConnectionInit remote function. So we are adding the prefix on to the message type. Then the messages will be automatically dispatched to relevant remote methods if we have defined that function. If you want to know further about this dispatching mechanism, you can go to Ballerina WebSocket spec. So in our case, we have connection init message and it will be dispatched to the on connection init remote method. So what we have to do is we have to implement that remote method. So in the remote method, what we should do is if we receive a connection init, we simply return a connection ACK. But if the client sends the connection init more than once, we must return too many initialization requests close frame record. In the Ballerina, that's how we can implement that logic. Next, we need to handle ping messages. Based on our dispatcher logic, when we receive a message with type ping, it should be dispatched to onPing remote method. But here's the thing, onPing is actually a special remote method that designed to handle WebSocket ping control frames, not application data frames. In our case, the ping message is application level data. So we need to handle it differently. Instead of using onPing, we will use the onPing message remote method. And to make that work, we will override the default dispatching behavior by using the dispatcher config annotation. In the onPing message, if we receive a ping message, we will simply return a ping message to the client. Next, we have to handle subscribe messages. Subscribe messages are dispatched to the onSubscribe remote method. When a client wants to start a subscription, it must send a unique ID with the request. And if that ID is already being used, we must send a subscriber already exists close frame record. Also, it is important to note that the subscription operations can only begin after successful connection initialization. If a client tries to subscribe before the connection initialization, we must send the unauthorized close frame record. While the subscription is active, the service can send three types of messages. We send next, we send next messages to send subscription result, complete message to indicate that the subscription has ended, or we send an error message if something goes wrong. All of these messages are sent as a stream, so the service can continuously push data to the client over time. So actually this streaming approach is what enables real-time updates, and it is one of the key reasons why GraphQL subscriptions are so useful when combined with WebSocket connections. Also, one important thing to note is that the client can subscribe to multiple different operations at the same time. This means the client will be receiving multiple streams of data all at once. To keep track of which message belong to which subscription, both the request and response messages include a field called ID. This is the unique ID we have discussed earlier. So the client uses this ID to match the incoming messages to corresponding subscription result. In the WebSocket service configuration, we have an attribute called dispatcher stream ID. Here we tell the service which field, in our case the ID, is used to identify and group the stream messages. So even though the service itself don't actually need this value to function properly, it is very helpful when we are generating the WebSocket client later. Alright, so far we have seen how the service handles different types of messages like connection, init, ping, and subscribe. If you like to take a closer look at the full code, you can find the GitHub link in the description below. Now, Let's generate a sync API specification for this WebSocket service and see how the GraphQL over WebSocket subprotocol is actually represented in the spec. Now, let's generate the sync API specification using Ballerina, the sync API tool. So, we will run this command. In the input flag tells us the specific service file, in our case listener.bal, and the protocol tells the tool that we are working with the WebSocket. As you can see, the spec generated successfully. Here is the generated spec which follows the Sync API 2.5 version. If we scroll down, you will notice it clearly documents all the request and response types used by our service. For an example, if we look at the connection init, you can see under the custom extension X responses, we have defined all the possible responses to connection init message, including connection hack, too many initialization request, and invalid message. This invalid message is the close frame that we are sending when payload binding error occurs, as defined in the protocol. Then let's see how the connection init schema is represented. Here's the connection init schema where we have the type field and our payload field. Next, let's take a look at how close frames are defined in the Sync API spec. For example, here we have too many initialization request close frame. If we go to the schema, we can see there are three fields: status code, the reason, and there is a new field called frame type. So what is frame type? Well, this field is used to distinguish a close frame from a regular message. If the frame type is set to close, we know it's a close frame. But how does the client or tooling reading this spec know about this behavior? To make that clear, we will introduce a custom extension called Ballerina WebSocket Close Frame. This extension tells readers when inspecting the message, check for the body for a field name frame type, and if its value is set to close, then treat it as a close frame. This way, close frames are clearly documented and easily identifiable from the other normal messages. Alright, now our spec is ready. It's time for generating the client. We can simply use this following command where we have to mention our spec file and our expected directory for generating the client. As you can see, our client has been generated successfully. We have client.bal, types.bal, and utils.bal. If we open the types.bal, you will find all the request and response types defined here. One important thing to notice is you won't see close frame records here. That's because from the client perspective, close frames are not handled as regular messages. Instead, they are treated as errors. So when the server sends a close frame like too many initialization requests, the client will receive it as an error and handle it accordingly. Now let's take a closer look at the generated client. Here you will see a method called doConnectionInit. If you remember, on the server side we had a method called onConnectionInit, which handles the connection init messages. On the client side, we have doConnectionInit, which sends the connection init messages to the server. It takes a connection init record as input and it returns a connection hack as the response. You will also notice a timeout parameter. This defines how long the client will wait for a response from the server. And just like do connection init, you will find a corresponding client method for each remote method defined in the service. These methods makes it is easier to interact with the server. Alright, finally let's see how to use this generated client in action. Here is a sample test function I wrote to try out the connection init flow. First, we initialize the client using a new keyword. Then we call the doConnectionAid method by passing connection init record and a timeout value. In this case, the timeout value is a constant. Then we print the result. So this is the main function I wrote to try out the test cases. Let's run one test case and see how it works. First, we have to run the service. Let's run the service by using Ballerina command. And then we can run the client. We want the first test case, the successful connection initialization. As you can see, we have successfully received the connection at message. Let's take a look at another sample. Here we also initialize the client and do a connection in it, then we do a subscribe. For the subscribe, we have to pass a subscribe message. And then finally, we will use the print result util function to print the response. Let's see this in action. So we want the scenario number 5. So as you can see, we are successfully receiving the 4 next frames, and finally we have received the complete message. And that's bring us to end of the video. Let's quickly recap what we have accomplished. First, we have implemented GraphQL-over-WebSocket subprotocol using Ballerina. Then we have generated an async API spec that fully captures the semantics of the protocol. And finally, we have used that spec to generate a fully functional client capable of handling real-time GraphQL subscriptions. You can find all the source code in the GitHub repo. Thanks for watching, and I'm Ayash. See you in the next one.